Good, good morning to everyone. The lecture 3 on design of machine elements is fits and tolerances. There are three types of fit: clearance fit, interference fit, and transition fit. So, in the fit is defined as the degree of looseness or tightness between two matting parts. Here, the two matting parts are one is a hole and another one is a shaft. An example for the hole and shaft is a cylinder and piston assembly in an IC engine. In an IC engine, the cylinder have a hole and the piston is a shaft. So, in the clearance fit in an IC engine assembly, and it should have the cylinder and piston should have some clearance in order for the movement of piston inside the cylinder. It should have some clearance. Otherwise, it will not be used. So, the cylinder and piston assembly is an example for clearance fit. Suppose if we are making 1000 cylinders separately and 1000 shafts separately in a manufacturing system, so all the shaft, all the holes should have tolerance, all the cylinders should have tolerance, that is, it is greater than the tolerance of the shaft. Then only there may be some clearance will be in between the hole and the shaft. Otherwise, it will interfere with each other. So this is a shaft. The shaft, the basic size of shaft is the from the this to this one, the basic size of shaft. This is the basic size of shaft. Okay, and this red color shows that the tolerance for the shaft, and this is the basic size of hole, and this red color shows a basic size of that is a tolerance for the hole. So this is a minimum size of hole and this is a maximum size of hole, and the top one is a minimum size of hole and the maximum size of hole. So minimum size of shaft and maximum size of shaft. So there is a clearance. Even then there is a clearance. If you are making 1000 components, some components, all the components, almost all the components are within this, all the holes are within this limit and all the shafts are within this limit. So there is a clearance. This clearance is called as minimum clearance, and maximum clearance is maximum size of the hole minus minimum size of the shaft is the hole tolerance. This is a maximum clearance. Minimum clearance is maximum size of shaft and the minimum size of hole is the difference between the two is called as the minimum clearance. This is a maximum clearance. So this is about the clearance fit. Then we will go for the interference fit. In the interference fit, that is, in the interference fit, this is a minimum hole and this is a maximum hole. Okay. And the minimum shaft is greater than that of the maximum hole diameter. So this fit, in this fit, the two components, that is the hole and the shaft, have to be inserted by means of applying some force, like by means of using hammer or any other external force only this type of fit can be made. So this type of fit is called as interference fit. So in this case, so this is the minimum interference. So the maximum hole minus minimum shaft is said to be the minimum interference, but the interference will be between this limit to that limit. So this is the maximum interference. Maximum interference equal to minimum hole minus maximum shaft. Okay, the difference between the two is said to be the interference fit. In the transition fit, we are making 1000 holes shaft and 1000 holes and 1000 shafts. Okay, some components may lie between the, some components may be clearance fit and some components will come under interference fit. This type of fit is called as transition fit. Okay, so some components will be of clearance fit and some assemblies will be of interference fit. This type of fit is called as interference transition fit. So clearance fit is the amount by which actual size of the shaft is less than the actual size of hole. So there is some clearance. In the interference fit, actual size of shaft is larger than the actual size of hole. Okay, here shaft size is greater, hole size is lesser. So it is fit by interference by applying some force. Transition fit, either it will be of clearance fit or it will be of interference fit. Okay, we'll see a small problem. The dimensions of matting parts according to basic hole system are given as follows. Hole 25.00 mm and 25.02 mm. Minimum size of hole is 25 mm and maximum size is 25.02 mm. The shaft size is maximum dimension is 24.97 mm. Minimum dimension of shaft is 24.95 mm. Now we find the hole tolerance. Hole tolerance is that is the maximum size of hole minus minimum size of hole is a hole tolerance. 25.02 minus 25.00 is a hole tolerance, which is equal to 0.02 mm. And shaft tolerance. The shaft tolerance, maximum size of shaft minus minimum size of shaft, 24.97 minus 24.95 is equal to 0.02 mm is the shaft tolerance. And allowance equal to lower limit of hole, that is allowance is that is minimum clearance equal to minimum hole minus minimum maximum shaft, 25.00 minus 24.97. So the minimum clearance equal to 0.03 mm. Maximum clearance is 25.02 minus 24.97, which is equal to 0.07 mm. So in this case, so 40 H8 F7 is a fit. 40 is a 40 mm. 40 mm diameter of the shaft is 40 mm. The tolerances are H8 and F7. So we have to take, you can find the values here. A formula is used to calculate the tolerance values for the shaft for this dimension. But in actual practice, but by using the PSC design data book, you can calculate the values H8 and F7 from the data book, and you can calculate the whole system for shaft as well as for the hole. You can find the dimensions by means of the data book. This type of formulas are not essential. Next, direct bending and torsional stress equations. So this is a review of different types of stresses that we have studied in the strength of material subject. Okay, these formulas are also available in PSC design data book page number 7.1. So stress, first tensile stress. So for the tensile stress, the formula is sigma equal to P by A. Okay, sigma equal to P by A. P equal to sigma is equal to tensile stress. P is a load and A is a area. So strain is defined by the symbol E or epsilon. Epsilon equal to del L by L, that is dl by L. dl is change in length by original length, that is called strain. So Young's modulus or modulus of elasticity equal to sigma by E, that is stress by strain equal to E, capital E. So the tensile stress, the definition for tensile stress is the resistance offered by the material against deformation when it is subjected to tensile loading is said to be the tensile stress. Okay, when the material is subjected to tensile load, when the material offers some, so here you can see the material offers some stress, material offers some resistance. That resistance is called as tensile stress. So this is shown by sigma T. It offers some resistance against failure. Okay, resistance against deformation. So this type of stress is called as tensile stress when it is subjected to tensile load. Then compressive load. So compressive stress when it is subjected to compressive load and the material offers some stress against deformation, that is against the compression of the material. So that stress is called as compressive stress, sigma c. Okay, the p is a compressive force, and p by a, area of cross section perpendicular to the axis. So sigma equal to compressive stress is also calculated using the formula sigma equal to p by a, load by area. But there are so many different types of stresses are available. Bending stress, okay, bending stress, when a material is subjected to bending load, okay, the material will bend, that is it will sag, the material will sag or it will hog, okay. This type of stress is called as bending stress. So bending stress, it is calculated using the bending equation, m by I equal to sigma by y equal to E by R. So m is the bending moment, I is equal to I is mass moment of inertia. Mass moment of inertia equal to dq by 12 for rectangular cross section and pi by 60 for d power for circular cross section. M by I equal to sigma by y. Sigma equal to stress, y equal to distance of extreme fiber from the center. Then sigma by y equal to E by R. E is modulus of elasticity or Young's modulus. R is R equal to y by y equal to R by 2. Okay, R equal to y by 2. Okay. Then torsional stress equations. Okay, when a material is subjected to torsional shear stresses, rotational shaft is subjected to torsional shear stress as well as bending stress. So T by J, it is given by the torsional stress equation. T by J equal to tau by R equal to C theta by L. T by J, T is torque, J is polar moment of inertia. Polar moment of inertia equal to Ixx plus Iyy, okay, which is equal to pi with 32 T power 4. J equal to pi with 32 T power 4 circular shaft. And T by J equal to tau by R. Tau is equal to shear stress, torsional shear stress, R equal to radius equal to C theta by L. C is modulus of rigidity, theta angle of rotation, C theta by L. L is the length of the shaft. Okay. Different types of load. The types of loads are there are three different types of load: dead load, live or variable load, suddenly applied load or shock load, and impact load. Dead steady load, the load will not change in direction. For example, in a building, the load of beams will not vary. Then live or variable load, the variable load will not, live or variable load, when it changes, it will change its dimensions continuously. For example, when a crankshaft in an IC engine, when a crankshaft rotates, for half of the cycle it is subjected to tensile load, remaining half of the cycle it is subjected to variable, it is subjected to compressive load. So the first half it is tensile, second half it is compressive. So it is variable. So the load is variable load. Suddenly applied or shock load. Suddenly applied load, when a load is applied suddenly or shock, it is called as suddenly applied load. And impact load, when a load is applied with an velocity, it is called as an impact load. Okay, this is a simple problem. A cast iron link is required to transmit a steady tensile load of 45 kN. Find the tensile stress induced in the link material at sections AA and BB. Okay, so tensile stress induced at section AA. Okay, this is section AA. It is of rectangular in section. So the tensile stress formula is sigma equal to P by A. So P equal to 45 kilonewton, 45 into 10 power 3. Okay, and area equal to rectangular cross section area equal to 45 into 20. So it is 900. So it is 50 megapascal. Tensile stress section BB is equal to, it is of this section, that is it is a rectangular section but it has a hole. So 20 into 75 minus 40, which is equal to 700 mm square. Load is 45 into 10 power 3 divided by 700. So it is equal to 64.3 megapascal. Okay, thank you.